Welcome, students, to the first part of lesson 1 in the syllabus of class 11 physics, physical world. In this lesson, we will be focusing on the following topics one by one. What is science? Steps involved in scientific method. What is physics? Scope and excitement of physics. Physics in connection to society, fundamental forces in nature, and lastly, the conservation laws. So, these topics will be dealt in this first chapter of class 11 physics. To begin with, what is science? Now, you might be a bit surprised that after studying this subject for so many years, why this question is being asked right now. What is science? All of us are living in an age dominated by science. We all need to develop a scientific temperament. Anything that we observe around us is so closely related to this subject, science. So, if we are so dependent on this subject, do we really need to find out an answer to this question? We all know what is science. The quest for knowing something, the curiosity to learn something new through our observations, through our experiences, whatever we understand, the way we perceive, the way we analyze, everything is science. So, let us define what is science. Science is a systematic enterprise that builds and organizes knowledge in the form of testable explanations and predictions about the universe. In an older and closely related meaning, science also refers to a body of knowledge itself of the type that can be rationally explained and reliably applied. A practitioner of science is known as a scientist. Humans have always been curious about the world around them. The night sky with its bright celestial objects has fascinated humans since time immemorial. The regular repetitions of the day and night, the annual cycle of seasons, the eclipses, the tides, the volcanoes, the rainbow have always been a source of wonder. The world has an astonishing variety of materials and a bewildering diversity of life and behavior. The inquiring and imaginative human mind has responded to the wonder and awe of nature in different ways. One kind of response from the earliest times have been to observe the physical environment carefully, look for any meaningful patterns and relations in natural phenomena, and build and use new tools to interact with nature. This human endeavor led in course of time to modern science and technology. The word science originates from the Latin word scientia, meaning to know. The Sanskrit word vigyan and the Arabic word ilm convey similar meaning, namely knowledge. Science, in a broad sense, is as old as human species. The early civilizations of Egypt, India, China, Greece, Mesopotamia, and many others made vital contributions to its progress. From the 16th century onwards, great strides were made in science in Europe. By the middle of the 20th century, science had become a truly international enterprise, with many cultures and countries contributing to its rapid growth. The knowledge which man has gained through observations and experiments, when organized systematically, is called science. Science is thus a systematic attempt to understand natural phenomena in as much detail and depth as possible, and use the knowledge so gained to predict, modify, and control phenomena. Science is exploring, experimenting, and predicting from what we see around us. The curiosity to learn about the world, unraveling the secrets of nature, is the first step towards the discovery of science. Scientific attitude and scientific method. The scientific method involves several interconnected steps: systematic observations, controlled experiments, qualitative and quantitative reasoning, mathematical modeling, prediction and verification or falsification of theories. Speculation and conjecture also have a place in science, but ultimately, a scientific theory to be acceptable must be verified by relevant observations or experiments. The interplay of theory and observation for experiment is basic to the progress of science. Science is ever dynamic. There is no final theory in science and no unquestioned authority among scientists. As observations improve in detail and precision or experiments yield new results, theories must account for them, if necessary, by introducing modifications. Sometimes the modifications may not be drastic and may lie within the framework of existing theory. For example, when Johannes Kepler examined the extensive data on planetary motion collected by Tycho Brahe, the planetary circular orbits in heliocentric theory, imagined by Nicholas Copernicus, had to be replaced by elliptical orbits to fit the data better. Occasionally, however, the existing theory is simply unable to explain new observations. This causes a major upheaval in science. Now, let me tell you, in the beginning of the 20th century, it was realized that Newtonian mechanics, till then a very successful theory, could not explain some of the most basic features of atomic phenomena. Similarly, the then accepted wave picture of light failed to explain the photoelectric effect properly. This led to the development of quantum mechanics to deal with atomic and molecular phenomena. What is physics? A way of describing the physical world. Physics comes from the Greek word physis, meaning nature, and the Latin physica, meaning natural things. So, physics is understanding the behavior and structure of matter. It deals with how and why matter and energy act as they do. Physics is a basic discipline in the category of natural sciences, which also includes other disciplines like chemistry and biology. Its Sanskrit equivalent is bhautiki, that is used to refer to the study of the physical world. A precise definition of this discipline is neither possible nor necessary. We can broadly describe physics as a study of the basic laws of nature and their manifestation in different natural phenomena. Now, here we remark on two principal thrusts in physics: unification and reductionism. One large question about scientific theories that excites philosophical and scientific attention concerns the possibility of producing a single theory that will encompass the domains of all the sciences. Many thinkers are attracted by the idea of a unified science, or by the view that the sciences form a hierarchy. Like, for example, chemical reactions themselves involve the forming and breaking of bonds, and these are matters of microphysics. A complete account of those ultimate constituents and their interactions would thus amount to a theory of everything. In physics, we attempt to explain diverse physical phenomena in terms of a few concepts and laws. The effort is to see the physical world as manifestation of some universal laws in different domains and conditions. For example, the same law of gravitation given by Sir Isaac Newton describes the fall of an apple to the ground, the motion of the moon around the earth, and the motion of planets around the sun. Similarly, the basic laws of electromagnetism, as given by James Clerk Maxwell's equations, govern all electric and magnetic phenomena. Reductionism is a philosophical position which holds that a complex system is nothing but the sum of its parts, and that an account of it can be reduced to accounts of individual constituents. This can be said of objects, phenomena, explanation, theories, and meanings. A related effort is to derive the properties of a bigger, more complex system from the properties and interactions of its constituent simpler parts. This approach is called reductionism and is at the heart of physics. For example, the subject of thermodynamics, developed in the 19th century, deals with bulk systems in terms of macroscopic quantities such as temperature, internal energy, entropy. Subsequently, the subjects of kinetic theory and statistical mechanics interpreted these quantities in terms of the properties of the molecular constituents of the bulk system. In particular, the temperature was seen to be related to the average kinetic energy of molecules of the system. These are the different branches of physics. We can get some idea of the scope of physics by looking at its various sub-disciplines. Basically, there are two domains of interest, macroscopic and microscopic. The macroscopic domain includes phenomena at the laboratory, terrestrial and astronomical scales. The microscopic domain includes atomic, molecular, and nuclear phenomena. Classical physics deals mainly with macroscopic phenomena and includes subjects like mechanics, that is motion and its causes, electrodynamics, optics, and thermodynamics. Mechanics founded on Newton's laws of motion and the law of gravitation is concerned with the motion or equilibrium of particles, rigid and deformable bodies, and general system of particles. The propulsion of a rocket by a jet of ejecting gases, propagation of water waves or sound waves in air, the equilibrium of a bent rod under a load, etc. are problems of mechanics. Electrodynamics deals with electric and magnetic phenomena associated with charged and magnetic bodies. Its basic laws were given by Coulomb, Oersted, Ampere, and Faraday, and encapsulated by Maxwell in his famous set of equations. The motion of a current carrying conductor in a magnetic field, the response of a circuit to an AC voltage, the working of an antenna, the propagation of radio waves in the ionosphere are problems of electrodynamics. Optics deals with the phenomena involving light, the working of telescopes and microscopes, colors exhibited by thin films are topics in optics. Thermodynamics, in contrast to mechanics, does not deal with the motion of bodies as a whole. Rather, it deals with systems in macroscopic equilibrium and is concerned with changes in internal energy, temperature, entropy through external work and transfer of heat. The efficiency of heat engines and refrigerators, the direction of a physical or chemical process are problems of interest in thermodynamics. Now, coming to the microscopic domain of physics that deals with the constitution and structure of matter at the minute scales of atoms and nuclei and even lower scales of length, and their interaction with different probes such as electrons, photons, and other elementary particles. Classical physics is inadequate to handle this domain, and quantum theory is currently accepted as the proper framework for explaining microscopic phenomena. Overall, the edifice of physics is beautiful and imposing, and you will appreciate it more as you pursue the subject. You can now see that the scope of physics is truly vast. It covers a tremendous range of magnitude of physical quantities like length, mass, time, energy, etc. At one end, it studies phenomena at the very small scale of length, say 10 to the power minus 14 meter or even less, involving electrons, protons, etc. And on the other hand, it deals with astronomical phenomena at the scale of galaxies or even the entire universe, whose extent is of the order of 10 to the power 26 meter. Just imagine that two length scales differ by a factor of 10 to the power 40 or even more. The range of time scales can be obtained by dividing the length scales by the speed of light. 10 to the power minus 22 seconds to 10 to the power 18 seconds. The range of masses goes from say 10 to the power minus 30 kg, that is the mass of an electron, to 10 to the power 55 kg, that is mass of observable universe. Terrestrial phenomena like somewhere in the middle of this range. Physics is exciting in many ways. To some people, the excitement comes from the elegance and universality of its basic theories. From the fact that a few basic concepts and laws can explain phenomena covering a large range of magnitude of physical quantities. To some others, the challenge in carrying out imaginative new experiments to unlock the secrets of nature, to verify or refute theories, is thrilling. Applied physics is equally demanding. Application and exploitation of physical laws to make useful devices is the most interesting and exciting part and requires great ingenuity and persistence of effort. What lies behind the phenomenal progress of physics in the last few centuries? Great progress usually accompanies changes in our basic perceptions. First, it was realized that for scientific progress, only qualitative thinking, though no doubt important, is not enough. Quantitative measurement is central to the growth of science, especially physics, because the laws of nature happen to be expressible in precise mathematical equations. The second most important insight was that the basic laws of physics are universal. The same laws apply in widely different contexts. Lastly, the strategy of approximation turned out to be very successful. Most observed phenomena in daily life are rather complicated manifestations of the basic laws. Scientists recognize the importance of extracting the essential features of a phenomenon from its less significant aspects. It is not practical to take into account all the complexities of a phenomenon in one go. A good strategy is to focus first on the essential features, discover the basic principles, and then introduce corrections to build a more refined theory of the phenomena. The connection between physics, technology, and society can be seen in many examples. The discipline of thermodynamics arose from the need to understand and improve the working of heat engines. The steam engine, as we know, is inseparable from the Industrial Revolution in England in the 18th century, which had great impact on the course of human civilization. Sometimes technology gives rise to new physics. At other times, physics generates new technology. An example of the latter is the wireless communication technology that followed the discovery of the basic laws of electricity and magnetism in the 19th century. The applications of physics are not always easy to foresee. As late as 1933, the great physicist Ernest Rutherford had dismissed the possibility of tapping energy from atoms, but only a few years later in 1938, Hahn and Meitner discovered the phenomenon of neutron induced fission of uranium. which would serve as the basis of nuclear power reactors and nuclear weapons. Yet another important example of physics giving rise to technology is the silicon chip that triggered the computer revolution in the last 3 decades of the 20th century. A most significant area to which physics has and will contribute is the development of alternative energy resources. The fossil fuels of the planet are dwindling fast, and there is an urgent need to discover new and affordable sources of energy. Considerable progress has already been made in this direction, but much more is still to be accomplished. Talking about the fundamental forces in nature, we all have an intuitive notion of force. In our experience, force is needed to push, carry, or throw objects, deform, or break them. We also experience the impact of forces on us, like when we move objects, when a moving object hits us, or we are in a merry-go-round. Going from this intuitive notion to the proper scientific concept of force is not a trivial matter. Early thinkers like Aristotle had wrong ideas about it. The correct notion of force was arrived at by Isaac Newton in his famous laws of motion. He also gave an explicit form for the force for gravitational attraction between two bodies. In the macroscopic world, besides the gravitational force, we encounter several kinds of forces. Muscular force, contact forces between bodies, friction, which is also a contact force, the forces exerted by compressed or elongated springs and taut strings and ropes that we refer to as tension, the force of buoyancy and viscous force when solids are in contact with fluids, the force due to pressure of a fluid, the force due to surface tension of a liquid, and so on. There are also forces involving charged and magnetic bodies. In the microscopic domain, again, we have electric and magnetic forces, nuclear forces involving protons and neutrons, interatomic and intermolecular forces. A great insight of the 20th century physics is that these different forces occurring in different contexts actually arise from only a small number of fundamental forces in nature. For example, the elastic spring force arises due to the net attraction or repulsion between the neighboring atoms of the spring when the spring is elongated or compressed. This net attraction or repulsion can be traced to the unbalanced sum of electric forces between the charged constituents of the atoms. In principle, this means that the laws for derived forces, such as spring force, friction, are not independent of the laws of fundamental forces in nature. At the present stage of our understanding, we know of four fundamental forces in nature: gravitational force, electromagnetic force, strong nuclear force, and weak nuclear force. So, we'll be discussing them one by one in our next class. Thank you.